So up to now basically we have discussed about the voltage source inverter. So in the voltage source inverter we have studied which is single phase and also the three phase. So in the single phase we have studied about the single phase half bridge voltage source inverter and also the single phase full bridge voltage source inverter. And also we have studied about the PWM technique. And also we have learned about the in the three phase 180-degree mode of operation and also the 180-degree mode of operation. So now, we have successfully completed all the voltage source inverter. So now we are going to move forward to study what is the current source inverter. So current source inverter I am going to tell you. So current source inverter means I have already told you here you need a stiff amount of, means you need a constant current at the input. So we are going to make a combination of the ideal voltage source and also an inductor. So this is going to act like a constant current source at the input. And I have already told you there are no freewheeling diodes. Freewheeling diodes are not at all necessary in the current source inverter. So there are no freewheeling diodes, only there are thyristors T1, T2, T3 and T4. So now this is the load I am going to make it here. Let me assume the load is a parallel combination of the resistor and the capacitor. Let me assume the load voltage is plus or minus V0. The load current is I0. And this is called as the input voltage. So this is called as the input voltage and this is the output voltage. And let me, I have already told you here, output current is independent of the load elements, whereas the output voltage is going to depend upon the load elements. This is the important points in the current source inverter. So now let us do the analysis of this circuit. So you can see clearly now here what I am doing is here. See, I am going to on two thyristors T1 and T2 in this time. So therefore then I am going to off the T3 and T4, means complementary fashion. So if I am going to on T1 and T2 means I am going to off T3 and T4. Suppose if I am going to on T3 and T4 means I am going to on T1, T2. So this is the complementary way of doing the, we can say the complementary way of on the thyristors. So whenever I on T1, T2 means I am going to off T3, T4. So whenever I on T3, T4 means I am going to off T1, T2. So this procedure I am going to repeat again and again. So now here I want to find what is the value of the output voltage. So whenever T1 and T2 are on, so whenever the T1 and T2 are on, so we can simply say that by using the KVL we can get that whatever the input voltage is equal to the output voltage. So therefore the input voltage is always equal to the output voltage. So input voltage is in this manner, so therefore the output voltage will also be in the same manner. Whereas from in this region only T3, T4 are going to get conduct but not T1, T2. So whenever T3 and T4 are going to conduct, then definitely by the circuit you can say that V0 is equal to minus Vn. So therefore Vn is in this fashion. So minus Vn means reverse of this one. So therefore in this fashion. So therefore you can see clearly, so negative of the input voltage. So whenever T1 and T2 are on, then the output voltage is equal to Vn. Whereas T3 and T4 are on means the output voltage will be negative of the input voltage. So with the help of this one we can easily draw the graph. So this is the output voltage we are going to get and this is the input voltage we are going to get. Now let me draw what is the value of the output current. So whenever T1 and T2 are on, I have already told you very important point, which is I have already assumed the input current value is I0. So I have assumed the input current value is I0. So from the ideal inductor we are going to get a current which is I0, that is called the input current I am going to assume. So whenever the T1 and T2 are on, so output current is equal to I0. So output current is equal to I0. With the help of circuit diagram we can say whenever the T1 and T2 are on, output current is equal to I0. Whenever T3 and T4 are on, so therefore the output current will be negative of the input current. So output current will be negative of the input current, so therefore minus I0. So therefore whenever the T1 and T2 are on, simply we can say that the output current is equal to input current which is I0. Whereas if the T1 and T3 and T4 are on means the output current is the negative of the input current, so therefore minus I0. So this is the way that you are going to draw this diagram. So see, no matter whatever the load elements, always the output current is same for each and every load. But only thing is the voltage diagram is going to get changed. See, as I have already told you, simple meaning which is for a inductor, or we can say for a capacitor. So the expression is I is equal to CdV by dt. So whenever the current is a constant. So whenever the current is a constant, what you are going to get? Whenever the current is a constant means voltage is equal to integration of the current. So therefore simply we can say that we are going to get a straight line. So integration of a, we can say that it's like a ramp signal we are going to get. So for a integration of a DC signal we are going to get a ramp signal. So therefore this is the thing that we are going to get. So output voltage we are going to get in this fashion. So plus sign that means we are going to get in this format. Negative means we are going to get downward. So it is going to repeat. So therefore simply we can say that based on the output current we have figured out what is the value of the output voltage. So with the help of capacitor. So therefore this is the diagram that you are going to get. For plus I naught the voltage will be rising, whereas for minus I naught the voltage will be decaying. So therefore this is the manner it is going to happen. And I have already told you whenever a T1 and T2 are on, so output voltage is equal to input voltage. So same as this one. Whereas whenever the T3 and T4 are on, so we can say that output voltage is negative of the input voltage, or simply input voltage is the negative of the output voltage. So negative of the output voltage is the input voltage. So we are going to get in this manner. So with the help of this means if you know the output current, then you can easily find the output voltage, and if you know the output voltage, then you can easily figure out the input voltage. I have already told you the switches that whatever the switches we are going to assume is they are fully controllable. So whatever the switches you are going to assume in the inverters, they are fully controllable. So therefore they are basically bipolar, unilateral, and also fully controlled means they can block both the voltages. Means they should always block both the polarity of voltages, and also they are unilateral means only current is only in the one direction, and they are fully controllable. So therefore these are the properties that switches should be satisfied in order to use in an inverter. So they should block the positive voltage and also the negative voltage, and the current in those switches should be only in the one direction, and also they are fully controllable means the user can control both the on and off states of these switches. So only these switches which are to be used in the inverter. So the switches should be bipolar, it should be unilateral, and also it is fully controllable. So if any switches can satisfy these three properties, then only we have to use those switches in this inverter concepts. So therefore the switches, whatever the switches that you are going to use in the inverter should satisfy the three basic properties. It should be bipolar, it should be unilateral, and also it is a fully controllable. So bipolar means blocking both the voltages, unilateral means the current in the switches will be only in the one direction, and the fully controllable means simply the user can control both the on and off state of the switches. If any switches satisfying these three properties, then we say it is said to be used in the inverter concepts. And if you want to find what is the output, or you can say what is the relationship between the, if you want to find what is the relationship between the output voltage and the input voltage. So output voltage and the input voltage. So this is the output voltage. So the time period of the output voltage is T dot. So the time period of the output voltage and also the output current is T dot. So now I want to find what is the, we can say the time period of the input voltage. So simply see if this is the time period of the output voltage or the output current is T naught. So I want to find what is the time period of the input voltage. So we can say that 2 into Tin is equal to T naught. So 2 into Tin is equal to T naught. So simply we can say that if you go for the reciprocal of this one, so if you go for the reciprocal of this one, simply we are going to get that the frequency of the output voltage is equal to half of the frequency of the input voltage. So simply we can say that the frequency of the output voltage is equal to half of the frequency of the input voltage, or simply the frequency of the input voltage is equal to 2 times the frequency of the output voltage. So for output voltage or the output current, its time period is 2 times the time period of the input voltage. So T naught is equal to 2 into Tin. So if you do the reciprocal of these things, you are going to get the frequency of the output voltage or output current is half of the frequency of the input voltage or input current. So simply we can say that the T naught is equal to In simply indicates that the frequency of the output voltage or the output current is equal to half of the frequency of the input voltage. That is the meaning of this one. So we have here learned about the current source inverter also we have successfully completed. So now we are going to learn the single phase series inverter. So now we are going to study what is a single phase series inverter. So series inverter we are going to study. So now single phase series inverter means here This is circuit diagram of the single phase series inverter. So input we are going to consider it is a supply of Vs, and here we are going to use thyristor T1 and thyristor T2. So here we are going to use two thyristors T1 and T2. Here we are going to keep RLC load, which is R, L and C, and the current in this RLC I am going to assume it is I naught of T. So let me assume this is the load of RLC combination and this is the current I naught of T. So here whenever T1 and T2 are on, so whenever T1 and T2 are on, I am going to assume that resistive body is nearly 0. See, whenever the resistive body is nearly 0 means it's a very small value, and whenever T1 is on and T2 is off. So whenever T1 is on and T2 is off, we are going to get I naught of T is equal to ICP into sine of omega naught T, where ICP is equal to Vx into under root over C by L, whereas omega naught is equal to 1 by under root over LC. So these are the important points we are going to get whenever the T1 is on and T2 is off. So now here first I am going to turn on the T1. So whenever I am going to turn on the T1, so T2 is off. So I've already told you I am going to assume the resistance is very much small or negligible. So therefore the current I naught of T is equal to ICP into sine of omega naught T, and I have already told you there is no initial capacitor voltage. So therefore finally we are going to get ICP is equal to Vs into under root over C by L, or simply I naught of T is equal to Vs into under root over C by L into sine omega naught T, where omega naught is equal to 1 by under root over LC. So if you draw the diagram, we are going to get current in this fashion. So in this fashion we are going to get, I have already told you up to omega T is equal to pi only, the current will be positive. So up to here it is going to connect. So T1 is going to connect up to omega T is equal to pi. So T is equal to pi by omega, where 1 by omega is nothing but, because omega is equal to 1 by under root LC. So 1 by omega will be root into LC. So therefore pi into root LC is the time for which the thyristor T1 is going to get conduct. So after that current wants to be negative, but negative current should not go through the thyristor. So therefore thyristor will be off after this pi into root over LC. So up to certain time I am going to give you. So after this certain time, then again means up to this certain time, after this I am going to give back. So after this certain time, again I am going to give the thyristor T2 as on. So after this T1 is already off. So therefore I am going to turn on the T2. So whenever I am going to turn on the T2, then the current will be going in the reverse fashion, because here now the capacitor is going to deliver the current. So capacitor is going to deliver the current to the inductor. So because of that the current is going to change its direction. So the current is going to change its direction, because now the capacitor is going to deliver the energy to the inductor. So therefore the current direction is going to get changed, which is I naught of T is equal to minus ICP into sine omega naught T, where ICP is equal to Vs into under root over C by L into again omega naught is equal to 1 by under root over LC. So therefore now the current will be negative of the previous one. So same for again same time for which pi into under root over LC, again T2 is going to get conduct. After that again T2 is off. So for this time I am going to say this is TC. So here T1 is off and here T2 is off. So we can say that this is the overall time period. So this is the overall time period. So overall time period is equal to pi into under root over LC plus TC plus pi into under root over LC plus TC. So you can see clearly for this much amount of time T1 is connecting, for this much amount of time T2 is connecting. So these are the extra times that we need to consider. So therefore TC plus TC. So overall time T is equal to 2 into pi by omega naught plus TC, because omega naught is equal to 1 by under root over LC. So where TC is called as a circuit turn of time and TQ is called as a device turn of time. So this is called as a circuit turn of time, means you need to ensure this much amount of time is necessary to ensure that the T1 is perfectly off. Again this much amount of time is necessary to ensure that T2 is perfectly off. So this much amount of time is necessary to ensure that T1 is perfectly off, and this much amount of time is necessary to ensure that T2 is perfectly off. So TC is called as a circuit turn of time, whereas TQ is called as a device turn of time. So you know the overall time period of the output current. So now I want to find what is the frequency of the output current. So frequency is the reciprocal of the time period. So 1 by 2 into pi by omega naught plus TC. So this is the overall frequency of the output current. But I want to find what is the maximum value of the output, or we can say I want to find what is the maximum frequency of the output current. So which is equal to same this one, but now here in place of TC I need TQ, because TQ is called as the device turn off time. If denominator is very lower, then only the overall value will become maximum. So denominator will be minimum only when TC is equal to TQ, but practically TC will be always greater than TQ. So therefore, but we are going to assume, if you want the maximum value, you have to go for TC is equal to TQ. So for this one, we are going to get the maximum frequency of the output current is equal to 1 by 2 into pi by omega naught plus TQ. If you want the general frequency of the output current, which is equal to 1 by 2 into pi by omega naught plus TC. So TC is called as the circuit turn off time, but TQ is called as the device turn off time. So for this much amount of time, T1 is conducting. So after this much amount of time is ensured that T1 is perfectly off. Again T2 is going to conduct, and this much amount of time is ensuring that here T2 is off. So this is all about the single phase series inverter. So now we are going to study the single phase parallel inverter. So now we are going to study the single phase parallel inverter. We are going to study in a detailed manner. So single phase parallel inverter means this is the circuit of the single phase parallel inverter. So now we are going to discuss about the single phase parallel inverter. So single phase parallel inverter means, so this is the circuit diagram of the single phase parallel inverter. So these are the two transistors we are going to keep in this parallel fashion, and the input is a DC supply, and also we are going to keep a capacitor between these two things. Again we are going to keep basically this is like a transformer. So primary winding and the secondary winding. So this is the dotted terminal, and this is also dotted terminal. So when we are going to give a positive voltage Vs DC voltage across this circuit, then what is the output voltage we are going to figure out. Let me assume the turns ratio is 2:1. So now see, we are going to find this graph for the output voltage. So this is the circuit diagram. Now I am going to turn on the thyristor T1. So whenever I on the thyristor T1, so T2 is also off. So here you can see clearly from the circuit diagram, from this graph, so T1 is on and T2 is off. So whenever the T1 is on, so only the upper part of the primary winding is going to get conduct. So only the upper part of the primary winding is going to get conduct. So because of that, plus Vs we are going to get. So whenever the plus Vs, here also plus Vs. So plus Vs and plus Vs is the output voltage will be, the capacitor voltage will be 2 Vs. So therefore it will be going up to 2 Vs. Means the capacitor is going to charge to plus 2 Vs. But the output voltage will be half of the input voltage. So input voltage is capacitor voltage. So therefore half of the capacitor voltage will be just Vs. So therefore this is the nature of this one. You can see clearly when T1 is on and T2 is off. So this overall voltage is going to apply across this dot plus and minus. So this is plus and minus Vs. So same thing is going to induce here also. If dot is positive means here also positive. If down is negative means here also negative. So plus or minus Vs, plus or minus Vs. So the overall capacitor voltage is the summation of these two voltages. So we are going to get Vs plus Vs is 2 Vs. So this is the overall capacitor voltage 2 Vs. But we need only, as it is a transformer, so it is 2:1 turns ratio. So half of the primary voltage. So it will be Vs. So output voltage will be only up to Vs. So that is the same thing I have shown here. So output voltage, the capacitor voltage is rising from 0 to 2 Vs. Whereas here, the output voltage will be from 0 to Vs only, half of the input voltage. So after that, I am going to again, after some time, again I am going to turn on the T2. So when the T2 is turned on, then what is the nature of the capacitor voltage and the nature of the output voltage we are going to figure out. So what I told you, after some time I am going to turn on the T2 means I am going to turn off the T1. So here, then whatever the capacitor voltage, whatever the supply voltage is going to completely across this inductor. So this primary winding inductor. So if this is positive means this is also positive. So positive and negative. So positive and negative means the dotted is negative. So here also dotted is negative. So negative plus. So plus minus Vs, plus minus Vs. So overall capacitor voltage will be minus 2 Vs. So upper part is negative and down part is positive means the capacitor voltage will be minus 2 Vs. So therefore now the capacitor voltage is going to charge up to minus 2 Vs, but we need the output voltage which is half of the primary voltage. So therefore simply we are going to get the output voltage as minus Vs. You can see clearly when T2 is on, I have already told you the capacitor voltage is changing from plus 2 Vs to minus 2 Vs. So therefore the output voltage will be changing from plus Vs to minus Vs, means half of this capacitor voltage. So like this it will be again minus Vs until again T1 is on. So same thing again it is going to follow. So same again graph is going to follow for periodically. So this is the way that you need to trigger T1 and T2. So therefore you are going to get the output voltage is like a AC wave. So input is a DC wave, but the output you are going to get a AC wave. That is the function of the inverter. So inverter basic function is to convert a fixed DC voltage into AC voltage of variable frequency. So that is the basic function of an inverter. And I have already told you how to get the variable frequency at the output just by changing the reference voltage, reference signal. If you are going to change the frequency, then definitely you are going to change the frequency of the output voltage. So only thing that we can simply say that the frequency of the output voltage is equal to the frequency of the reference signal. But whereas by changing the carrier signal frequency, we are going to only change the number of pulses in half of the cycle of the V0 of t. So this is the simple meaning I am trying to say, that as it is a parallel inverter means the two thyristors are somewhat connected in a parallel fashion. That is the reason we are going to call it as a single phase parallel inverter. So by this circuit what we have got is input is a fixed DC, but the output we are going to get a AC value or AC signal. This is the meaning of this circuit. Now I will discuss some more important formulas regarding the inverters. Some more important formulas in the inverters. So the first thing is we are going to study the Fourier analysis of this graph. So now you are going to see this graph here. So we are going to do the Fourier analysis of this graph. So you can see clearly this is an odd signal. So as this is an odd signal, so you can see clearly here I have already told you the expression of this, as it is a periodic signal and also odd. So therefore A0 and AN are going to become 0 because the signal is an odd signal. So therefore A0 and AN is going to become 0. So only Vn is going to present. So after doing that we are going to get the final expression, which is V0 is equal to sigma n is equal to 1 3 comma 5 up to infinity 4 into the peak value, which is VDC by n pi into sine of n omega naught t, where omega naught is equal to 2 pi by t. So therefore this is called as the expression of this periodic signal in the terms of the Fourier series. So V0 is equal to sigma n is equal to 1 3 5 up to infinity 4 into VDC by n pi into sine n omega naught t. So you can see clearly, suppose if you substitute n is equal to 1, we are going to get the fundamental component. If you substitute n is equal to 3, we are going to get the third harmonic. And if we are going to substitute n is equal to 5, we are going to get the fifth harmonic, and it goes on up to infinity. So therefore only odd harmonics are going to present in this signal. So only odd harmonics are going to present in this signal. So now I want to find what is the RMS value of this overall signal. So RMS value of this overall output signal is equal to peak value, which is VDC. So the RMS value of this overall signal V0 is equal to peak value, which is VDC. So now I want to find what is the peak value of the fundamental component. I want to find what is the peak value of the fundamental component in the output voltage. So if you want to know what is the fundamental component, substitute n is equal to 1. So we are going to get the peak value, which is 4 into VDC by pi. So 4 by pi is nothing but 1.27 into VDC. So this is the peak value of the fundamental component of the output voltage. Suppose if you want to find what is the RMS value of the fundamental component of the output voltage is equal to peak value by root 2. So this is a peak value, just go for the division by root 2. So we are going to get finally 2 into root 2 by pi VDC. So this is the RMS value of the fundamental component of the output voltage. So now I want to find what is the distortion factor of this wave. So distortion factor is equal to the ratio of the fundamental component RMS value by the RMS value of the overall output signal. So the RMS value of the fundamental component of the output voltage by the RMS value of the overall output voltage. So we know the value of the RMS value of the fundamental component of the output voltage, which is 2 into root 2 by pi VDC, whereas the RMS value of the overall output signal is equal to VDC. So if we do the division of these two parameters, we are going to get finally 0.9. So 0.9 is the distortion factor of the output signal V0. So now I want to find, see, I can find even the RMS value in the other method also, which is V0 RMS square is equal to V01 RMS square plus V03 RMS square plus V05 RMS square up to goes on up to infinity. So simply the overall RMS value of the output signal is equal to under root over RMS value of the fundamental component whole square plus RMS value of the third component whole square plus RMS value of the fifth component whole square plus, and it goes on up to infinity. So this is by using the basic property. So if you want to find what is the RMS value of the overall signal is equal to under root over RMS value of the fundamental component whole square plus RMS value of the third component whole square plus RMS value of the fifth component whole square plus, and it goes on up to infinity. So now see, except fundamental remaining everything is called as the except fundamental remaining everything is said to be harmonic component. So therefore see, except fundamental remaining everything is said to be harmonic component RMS value, which is square. So therefore V0 RMS square is equal to V0 1 RMS square plus, so all these terms we are going to call this as the RMS value of the harmonic component. So RMS value of the harmonic component in the output voltage whole square. If you want to find what is the harmonic component RMS value, if you want to find what is the RMS value of the harmonic component present in the output signal is equal to under root over V0 3 RMS square plus V0 5 RMS square, and it goes on up to infinity. So this is the basic thing that you need to remember. So therefore finally you are going to get this expression. So now whereas THD, so THD is nothing but it's the ratio of the, so THD I have already told you, THD is nothing but it's the ratio of the RMS value of the harmonic voltage by the RMS value of the fundamental component. So listen carefully, what is the value of THD? So THD is equal to ratio of the harmonic, or we can say the RMS value of the harmonic voltage by the RMS value of the fundamental component. So listen carefully, THD is equal to, it is a ratio of the RMS value of the harmonic voltage by the RMS value of the fundamental component is equal to. So now here you can write this expression in this format also, means simply V0 H RMS you can write, which is under root over V0 RMS whole square minus V0 1 RMS whole square. So like that you can write, and after doing the simplification finally you are going to get like this. So I have already told you, which is this value, which is V0 1 RMS by V0 RMS is called as a G. So this overall value is 1 by G whole square minus 1. So simply we can say that THD is equal to under root over 1 by G whole square minus 1. So THD is equal to under root over 1 by G whole square minus 1. So you know the value of G, substitute here, and if you do a simplification finally you are going to get 0.483. 0.483 is the THD in this of the signal. So therefore simply we can say that simply G is called as a distortion factor. It is a ratio of the fundamental component RMS value by the RMS value of the overall signal, whereas THD is the ratio of the harmonic component of the, you can say, RMS value of the harmonic voltage by the RMS value of the fundamental component. So by using the simplification we are going to get THD is equal to under root over 1 by G whole square minus 1. Now we are going to study some more important points in the inverter. So in the inverter, I have already told you, in the inverter we are going to study two things, which are the voltage source inverter and also the current source inverter. So in the voltage source inverter we are going to study single phase. So single phase and also three phase. In the single phase we are going to study fixed voltage variable frequency. Fixed voltage variable frequency means the input is a fixed voltage and the output we are going to get variable frequency of AC nature. So here we are going to study two things, which are the half bridge and also full bridge. In the half bridge we are going to study for R load, L load, RL load and also RLC load. For full bridge also we are going to study for R load, L load, RL load and also RLC load. Whereas here another parameter, which is variable voltage and variable frequency, means the input voltage is variable and the output voltage is of variable frequency. So we are going to get in terms of PWM. So this is the method we are going to use for PWM. In the other ways, which are three phase, we are going to study 180-degree mode of conduction and also the 100-degree mode of conduction. So all these things we are going to study one after the another in a very detailed manner. So in the inverter we are going to study the two basic things, which are the voltage source inverter and also the current source inverter. In the voltage source inverter we will study about the single phase and also three phase. In the single phase, in fixed voltage with variable frequency, means input voltage is fixed, so but the output voltage is of AC nature and also variable frequency. So we are going to study half bridge and also full bridge. So in the half bridge we are going to study for R load, L load, RL load and also RLC load. And for full bridge, we are going to study for R load, L load, RL load, and RLC load. Whereas for variable voltage and variable frequency, we are going to study for PWM. And for three phase, we are going to study for 180-degree mode of conduction and also the 120-degree mode of conduction. And this is the current source inverter. So all these things we are going to study one after the another. So now we are going to study single phase off bridge inverter. So we are going to study basically single phase off bridge inverter. Single phase off bridge inverter. So here input, so this is a circuit diagram. So this is the circuit diagram of this single phase off bridge inverter. So basically inverter means the basic function of inverter is to convert fixed DC into variable frequency of AC nature. That is the inverter basic function. So we are going to keep an R load. So now we are going to keep an R load. So this is VDC by 2 and VDC by 2, and this is a switch S1 and switch S2, and this is the current in the switch 1. So this is the IASW, means it is the current in the switch, and this is the freewheeling diode and freewheeling diode. I have already told you freewheeling diodes are only used in the voltage source inverter. So this is the voltage source inverter. So only freewheeling diodes are used only in the voltage source inverter. So now there is a load I am going to connect here of R load. Let me assume this is plus or minus V naught of t. So this is current is I naught of t. So now we are going to learn about the single phase off bridge inverter. So this is the concept that we are going to learn, which is the single phase off bridge inverter. So in the single phase off bridge inverter, the first load we are going to discuss is the R load. So single phase off bridge inverter. So this is a circuit diagram of the single phase off bridge inverter. So here you can see clearly the supply voltage is VDC by 2, and this is VDC by 2. Here there are two switches, switch 1 and switch 2, with the freewheeling diodes D1 and D2. So only for the voltage source inverter only we need to use the freewheeling diodes, but not for the current source inverter. So let me assume this is ISW of t, means it is a switch current, whereas the source current is IS of t. Let me assume a load of pure resistive load. So therefore its output voltage is simply plus or minus V naught of t, and the output current is I naught of t. So now we are going to analyze each and every aspect in this circuit. So now we are going to basically analyze this circuit. So now we are going to do the analysis of this circuit. So what is the analysis of this circuit is here. First thing, we are going to assume that two switches are operated in the complementary fashion, or we can simply say that these switches are operated in the complementary fashion, means if one switch is on means the other switch is off. That is the meaning of this one. So two switches are operated in always in complementary fashion, and the switches are unidirectional switches. It's only the current can flow only in the one direction but not in the reverse direction. So these are the assumptions that we are going to consider, which is we are going to do the complementary function of the switches. If one switch is on means the other switch is off. So therefore again the switches are always unidirectional in nature. So only current travels only in the one direction but not in the reverse direction in these switches, where IS of t is called as the source current and ISW of t is called as the current in the switch, or simply switch current. So for 0 less than t less than t by 2, so for this much amount of time we are going to on the switch S1. So we are going to on the S1 switch and off the F2 switch. So therefore we are going to on the S1 switch and off the S2 switch, means if one is on means the other is off. It's a complementary way of doing this one. So when S1 is on and S2 is off, so therefore by using the KVL we are going to get V naught of t is equal to VDC by 2. So V naught of t is equal to VDC by 2 you are going to get, and I naught of t is equal to V naught by R, which is VDC by 2R. So VDC by 2R you are going to get the output current. So during t by 2 to t, so during t by 2 to t, you can see clearly that here S1 is off and S2 is on. So one is off means the other you should go for the on complementary way of doing the onning and offing of the switches. So if you apply the KVL, then we are going to get V naught of t is equal to minus VDC by 2 and I naught of t is equal to V naught by R, which is minus VDC by 2R. So simply we can say that here, so in this range we are going to get V naught of t is equal to minus VDC by 2 and I naught is equal to minus VDC by 2R. So now with the amount of given data, now I am going to plot the graph. So for 0 less than t by 2, so V naught is equal to plus VDC by 2 and I naught is equal to, which is plus VDC by 2R. Whereas t by 2 to capital T, so V naught is equal to minus VDC by 2 and I naught is equal to minus VDC by 2R. So from based on this we are going to plot this graph. So this is the output voltage we are going to get, and this is the output current we are going to get. You know, it is a square wave. So output voltage is a square wave. So therefore, the overall RMS value of the output voltage is equal to, which is VDC by 2. So VDC by 2 is the output RMS value, which is equal to 0.5 VDC. So 0.5 VDC is the RMS value of the output voltage. So if you want to find what is the expression of the output voltage, as the output voltage is a periodic signal, so you can write in terms of Fourier series, which is V naught of t is equal to sigma n is equal to 135 up to infinity 4 into the peak value, which is VDC by 2 by n pi sine of n omega naught t. So simply sigma n is equal to 135 up to infinity 4 into the peak value, which is VDC by 2 by n pi into sine of n omega naught t. So if you do a simplification, we are going to get sigma n is equal to 135 up to infinity 2 VDC by n pi into sine n omega naught t. So this we are going to get the output voltage in terms of Fourier series. So if you want to know what is the only fundamental output voltage, only fundamental output voltage if you want, then keep your n is equal to 1. Then you are going to get the fundamental component of the output voltage, which is 2 VDC by pi into sine omega naught t. And simply, if you want to know what is the fundamental output current, so fundamental output current is equal to fundamental output voltage by R. So you are going to get the fundamental output current is equal to VO1 of t by R. So you are going to get 2 VDC by pi R into sine of omega naught t. So this is your fundamental output current you are going to get. So now we are going to plot the fundamental output voltage and also fundamental output current we are going to plot. So the fundamental output voltage is equal to, so the fundamental output voltage is equal to this 2 VDC by pi into sine n sine omega naught t. So 2 VDC by pi into sine omega naught t is the fundamental output voltage. So this is the graph you are going to get. Whereas fundamental output current is, this is the expression, which is simply 2 IDC by, so simply fundamental output current is equal to 2 VDC by pi r into sine omega naught t. So this is the equation we are going to get. 2 VDC by pi r into sine omega naught t is the fundamental output you are going to get. So these are the two plots we have already drawn. So now the fundamental RMS value is equal to, means the RMS value of the fundamental output voltage is equal to, which is peak value by root 2. So 2 VDC by pi by root 2, we are going to get root 2 VDC by pi. So RMS value of the fundamental component of the output voltage, which is root 2 VDC by pi. Similarly, if you want to find what is the RMS value of the fundamental component of the output voltage, which is peak value by root 2, so we are going to get root 2 VDC by pi r, you are going to get. So based on this, I want to find what is the value of distortion factor based on the output voltage. So G is equal to distortion factor ratio of the RMS value of the fundamental component of the output voltage by RMS value of the overall output voltage. So the RMS value of the fundamental component of the output voltage, which is root 2 VDC by pi, whereas the RMS value of the overall output voltage is equal to the peak value which is VDC by 2. So if you do the ratio of these two things, we are going to get 0.9. So 0.9 is the distortion factor you are going to get. So now if you want to find what is the THD, is equal to under root over 1 by g whole square minus 1. So if you substitute g and if you solve this one, we are going to get 0.483 we are going to get. So THD is equal to 0.483 or simply 48.3%. So now you can see clearly the switch current is equal to, the current to the switch is equal to source current, because the freewheeling diodes are not at all conducting for pure R load. The freewheeling diodes are not at all conducting for the pure R load. So therefore, whatever the switch current in the S1 is equal to current through the source. So IS of t is equal to ISW of t. So therefore, ISW of t is equal to simply we can say it is I naught of t for 0 less than t less than t by 2. So for 0 less than t less than t by 2, see T1 S1 is conducting. So as S1 is conducting, so simply we can say that ISW of t is equal to I naught for 0 less than t less than t by 2, because here switch S1 is conducting, whereas is equal to 0 for t by 2 less than t, because in this region S2 is conducting whereas S1 is off. If S1 is off, then definitely the switch current is equal to 0. So therefore the switch current is equal to I naught of t for 0 less than t by 2, whereas it is equal to 0 for t by 2 less than capital T. So similarly, I want to plot what is the value of the fundamental component of the switch current. So similarly, I want to find what is the fundamental component of the switch current is equal to, which is equal to same the fundamental component for 0 less than t by 2, then the fundamental component of the output current, which is 2 VDC by pi r into sine omega naught t, is equal to 0 for t by 2 less than t. So simply we can say that here, simply we can say that the switch current, the fundamental component of the switch current T is equal to 2 VDC by pi r into sine of omega naught t for 0 less than t by 2, and it is equal to 0 for t by 2 less than t, because here the switch S2 is conducting, so switch S1 is off, so current is equal to 0, whereas here the switch S1 is conducting, so whatever the load current is the same as the current of the switch. So if you want fundamental current, it is equal to fundamental current of the load current. So in this thing, so now based on this, we are going to draw these diagrams of this both the things. So now you can see clearly the switch current is equal to source current. So for 0 less than t by 2, its value is equal to the load current. Its value is equal to load current, which is VDC by 2R. Whereas t by 2 to t less than t, its value is 0, because here S1 is not conducting, so only S2 is conducting, so its current is equal to 0. So therefore all the switch current is equal to source current. So if you want to find what is the fundamental component of the switch current is equal to, for 0 less than t by 2, in this region we can say that it is equal to the fundamental component of the output current. So the fundamental component of the output current is this manner. So therefore for 0 to t by 2, its value is equal to the fundamental component of the output current. Where t by 2 to t, the switch S1 is off, only switch S2 is connecting, so therefore the current will be 0. So therefore for this range it is equal to 0. So we have drawn what is the switch current and also the fundamental component of the switch current. So now you can see clearly, so the fundamental component of switch current is equal to the fundamental component of the source current, because they are always equal. So therefore the fundamental component of the switch current is equal to the fundamental component of the source current. So ISW01 of t means that the fundamental component of switch current, whereas IS01 of t means the fundamental component of the source current. So in resistive loads, diodes won't conduct. I have already told you, in the resistive loads, diodes won't conduct. So therefore, see, no diode is going to get conduct. So simply we can say the diode current is equal to 0. So diode current is always equal to 0. So now I am going to draw this on the graph. So always the diode current is equal to 0, because they are not at all conducting for pure resistive load. So you can see clearly the diode current is equal to 0 for all the time, because they are not even conducting. So now I want to find what is the average value of the source current. So average value of the source current is equal to the average value of the switch current, because both are same. So always the source current is equal to switch current. So therefore whatever the average value of the source current is equal to average value of the switch current is equal to. So you can see clearly from the graph. So from the graph, the switch current, if you want to find what is the average value, which is VDC by 2R into T by 2 by capital T. So if you solve this one, we are going to get VDC by 4R. So this is called as the average value of the switch current or the source current. So if you want to find what is the RMS value of the source current or the RMS value of the switch current is equal to, which is VDC by 2R into under root over T by 2 by T. So you are going to get finally VDC by 2 into root 2R. So this is the thing that you are going to get. So these two things we have calculated from the graph. Similarly, if you want to find what is the average value of the fundamental component of the switch current or the fundamental component of the source current, because both are equal, so simply we can say that the average value of the fundamental component of the switch current or the average value of the fundamental component of the source current, both are equal. So from the graph we can easily say that peak value by pi, which is 2 VDC by pi r by pi. So if you solve this one, we are going to get 2 VDC by pi square r. So peak value by pi vi, because it's the half wave rectifier signal. So therefore you are going to get this one. Similarly, if you want to find what is the RMS value of the fundamental component of the switch current or the fundamental component of the source current is equal to, see, peak value by 2. So peak value by 2 is nothing but 2 VDC by pi r by 2. So you are going to get VDC by pi r. So all these things we have calculated from the graphs itself. So now we are going to find what is the power across load due to fundamental components. So due to fundamental components, what is the power across the load we are going to figure out. So power across load due to fundamental components. So due to fundamental component of the output voltage and the fundamental component of the output current, what is the output voltage? How much amount of power consumed, that we are going to figure out. So the fundamental component of the output voltage is equal to V01 RMS into I01 RMS into cos phi 1. Means the RMS value of the fundamental component of the output voltage into the RMS value of the fundamental component of the output current into phase angle, cos of phase angle between the fundamental component of the output voltage and the fundamental component of the output current. So V01 RMS is called as the fundamental value of the fundamental component of the RMS output voltage, means the RMS value of the fundamental component of the output voltage, whereas I01 RMS means the RMS value of the fundamental output voltage. So RMS value of the fundamental output current and RMS value of the fundamental output voltage. So whereas phi 1, I have already told you the phase angle between the fundamental component of the output voltage and the fundamental component of the output current. So because it is the resistive load, there is no phase difference, so it is equal to 0 degree. So simply if you substitute cos 0 is 1, so therefore it is the RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the output current is equal to. So you can go like simple relation, which is the square of the fundamental component of the output voltage by R, or simply square of the current of the RMS value of the fundamental current into R. So simply we can say that the RMS value of the fundamental component of the output voltage whole square by R is equal to the RMS value of the fundamental component of the output voltage square into R. So you can go for any of these things, but we have already know, which is simply we can say that the RMS value of the fundamental component of the output voltage we have already figured out. So what is the RMS value of the fundamental component of the output voltage, which is root 2 VDC by pi. This value just now we have figured out. So substitute here, do the square and do the division by R. So you are going to get 2 VD square by pi square R. So this much amount of power is consumed by the load due to fundamental component of the output voltage and the fundamental component of the output current. And if you want to keep here the fundamental component of the RMS value of the output current, you also know, which is root 2 VDC by pi R. So substitute here and do the square and do the multiplication by R. Still you are going to get the same result, because all these values we have already figured it out. So simply we can say that cos phi 1, so cos phi 1 is called as the fundamental displacement factor. So cos phi 1 is called as a fundamental displacement factor. It is equal to 1 because here there is no phase difference. So therefore cos phi is called as a fundamental displacement factor, or it is a power factor of the phase, is the cause of angle between the fundamental output voltage and the fundamental output current. So this we are going to call it as the fundamental displacement factor. So now I want to find what is the fundamental power delivered by each source. So fundamental power delivered by each source. So what is the fundamental power delivered by each source? So what is the fundamental power delivered by each source? So which is equal to the fundamental power by source 1, because there are two sources. So therefore the fundamental power delivered by each source is equal to the supply voltages, which is VDC by 2 into the fundamental component of the source current average value we have taken. So therefore we can say that here VDC by 2 into average value of the fundamental component of the source current. So VDC by 2 into the average value of the fundamental component of the source current is equal to, so this value just now we have figured out, it is equal to the average value. So the average value of the fundamental component of the source current is equal to 2 VDC by pi square R. So if you substitute here, we are going to get finally VD square by pi square R. So therefore simply we can say that here VDC by 2 into average value of the fundamental component of the source current. This value just now we have figured out, which is equal to 2 VDC by pi square R. If you substitute here and do the multiplication, we are going to get VD square by pi square R. So there actually IS1 means simply we can say that IS01 or IS1 both are same. So this is the average value of the fundamental component of the source current. So this is called as the fundamental power, the fundamental power which is delivered by each source. So now the fundamental power delivered by both sources. So if you want to know what is the fundamental power delivered by both sources, as there are two sources, this you have to go for 2 times of each one. So this much amount of total power is delivered by this much amount of total fundamental power delivered by both sources. So this much amount of total fundamental power is delivered by both the sources. Just 2 times of this one. So 2 times of Vd square by pi square r. So you are going to get this much amount of power. It is equal to same as this one. So therefore we can say whatever the total fundamental power delivered by both the sources is equal to the total fundamental power which is absorbed by the load. So we can say that whatever the total fundamental power delivered by both the sources is consumed by the load. So we can say that simply that the total fundamental power delivered by both the sources is equal to the fundamental power which is consumed by the load. So simply listen carefully. The total fundamental power delivered by both the sources is equal to the total average power consumed by the loads because of the fundamental components. So this we are going to call it as the fundamental power delivered by both the sources, whereas P01 means fundamental output power received by load. So both are always equal. So whatever the overall fundamental power delivered by both the sources is consumed by the load by the fundamental component of the output voltage and the output current. Total power across load. So what is the total power across the load? So what is the total power? Means total average power consumed by the load. So total average power consumed by the load is equal to V0 RMS into I0 RMS into cos of phi. So V0 RMS into I0 RMS into cos phi. Because it is a pure resistive load. So there is no phase difference because both are same. So there is no phase difference between them. So therefore cos 0 is equal to 1. So V0 RMS and I0 RMS. So we can write it in another format which is V0 RMS square by R or simply I0 RMS square into R. But we know the value of V0 RMS. So V0 RMS value we have already figured out which is peak value which is VDC by 2. And I0 RMS value also we know which is peak value by peak value which is the peak value itself. So therefore simply we can say that here you know the peak values of both the graphs. You can substitute and do the simplification. We are going to get finally Vd square by 4R. So this is the overall average power consumed by the load. So this is the overall average power consumed by the load. So total power delivered by each source. So what is the total power delivered by each source? Each source, how much amount of total power it is delivering. So the total power delivered by each source is equal to VDC by 2 into the average value of the source current. So the average value of the source current just now we have figured out which is we have already know the value of the average value of the source current which is VDC by 4R. So VDC by 4R into VDC by 2 you are going to get VD square by 8R. So this much amount of overall power delivered by each source. So VD square by 8R. But what is the total power supplied by both the sources means 2 times of this value. So therefore you are going to get VD square by 4R. This is equal to output power. So therefore we can say that the total power supplied by both the sources is equal to consumed by the load. So simply we can say that the total power supplied by both the sources is equal to it is the power which is consumed by the load. That is the meaning of this one. So now we are going to learn about the load. Means now we are going to replace the resistive load by the inductive load and then we are going to do the analysis. This is the same previous circuit, just we have replaced the resistor by the pure inductive load, and the voltage across the inductive load is which is plus or minus V0 of t and is the current I0 of t. So I0 of t is the current in the inductor and this is the voltage across the inductor. So VDC by 2, S1, S2. So diodes D1 and D2 and this is the switch current, or we can say simply IS1 means the switch current and IS2 means the switch current in the switch 2. So now we are going to do the analysis of each and every aspect of this circuit diagram. Then we are going to do this one. Analysis. Generally for any load. So generally for any load we are going to give some basic things. So with the help of these things that you can easily able to understand the switching process. Generally for any load, when only S1 conducts, what is going to happen? So generally for any load, only when S1 conducts, so if you switch on the S1, then what you are going to get, which is V naught of t is greater than 0 and the I naught is also greater than 0, because the load is at charging mode. So therefore the output voltage is positive and also the output current is positive. Whereas only when only D1 conducts. So when only D1 conducts, what is going to happen? When only D1 conducts, we can simply say that here the output voltage is again positive, whereas the output current is negative. So output voltage is positive and the output current is negative with the help of the circuit diagram. Whereas when only S2 conducts, so when only S2 conducts, if you switch on the S2, then we can say that the output voltage is negative, and also the output current is also negative. So output voltage is negative and the output current is also negative. Whereas only when D2 conducts, means if you on the D2, then simply we can say that if only D2 conducts, we can simply say that the output voltage is negative and the output current is positive. So these are the things that you need to know from the circuit diagram. So with the help of these things, we are going to draw the graphs of the output voltage and also the output current. So we are going to draw the circuit diagram of the output voltage and the output current for this inductive load. So now I have already told you, irrespective of the load, for a single phase average voltage source inverter, the output voltage will be in this fashion. So for 0 to t by 2, its value is equal to VDC by 2, whereas t by 2 to t, its value will be minus VDC by 2. So irrespective of the load, the output voltage will be always constant. So now what I am going to do basically is here, as it's a pure inductive load, so if you apply a if you apply a DC voltage for a purely inductive load, what is going to happen? Because in an inductor, the expression of the voltage and current is equal to V is equal to L di by dt. So if you want current, it is the integration of the voltage. So for a constant voltage, we are going to get a ramp signal. So current will be in the ramp, but in an inductor, the current is going to lag by 90 degree. So therefore you have to go for 90 degree lag. So you are going to get in this fashion. So this is called as the inductive current. So it is going to lag the supply voltage by 90 degree or simply T by 4. So therefore this is T by 4, T by 2, 3T by 4 and T. So it is going to lag the input voltage by pi by 2. So this is the thing that you are going to get. So this is the maximum value of the output current. This is plus I naught max and this is a minus I naught max. So these are the maximum value of the output current, which is plus I naught max and minus I naught max. So this is the output voltage and this is the output current. In an inductor, I naught of t lags V naught of t by 90 degree. As I have already told you, in an inductor, the current is going to lag the voltage by 90 degree. So therefore the output current is going to lag the output voltage by the 90 degree. So now the conduction angle of, so now you can see clearly from 0 to t by 4. So from 0 to t by 4, the output voltage is positive and the output current is negative. So output voltage is positive and the output current is negative only when D1 conducts. So D1 is connecting from 0 to t by 4. Whereas from t by 4 to t by 2, you can see clearly the output voltage is positive and the output current is also positive. So both are positive only when S1 is conducting. Whereas t by 2 to 3t by 4, the output voltage is negative and the output current is positive. So the output voltage is negative and the output current is positive only when D2 conducts. Whereas from 3t by 4 to t, the output voltage is negative and the output current is also negative. So both are negative only when S2 conducts. So now we got the regions where the diodes and transistors are going to conduct. So we know each and everywhere where the switch is conducting and where the diodes are conducting. So same thing I have told you. Here V naught is positive and I naught is negative. So V naught is positive, I naught is negative means D1 is connecting. Here V naught is positive, I naught is positive. So both are positive means S1 is connecting. Here that V naught is negative whereas the I naught is positive. Then we can say that D2 is conducting. Whereas here V naught is negative and the I naught is also negative. So simply we can say that if both are negative means S2 is conducting. So we know in which regions that switches and diodes are going to conduct. So this is the conduction of each and every diode and the thyristor and the switches. So now the conduction angle of each diode. So we can see clearly the conduction angle of each diode is 90 degree. So the conduction angle of each diode is 90 degree. Whereas the conduction angle of both diodes is as one diode is going to conduct for 90 degree. So there are both diodes. So therefore 90 into 2 is 180 degree. So therefore the conduction angle of each diode is equal to 90 degree. Whereas the conduction angle of both diodes is equal to 180. Similarly, the conduction angle of each switch is 90 degree. Whereas the conduction angle of both thyristor or both switches is 180 degree. So simply we can say that each switch or each diode is connecting for only 90 degree. So both switches are going to connect for 180 degree, and similarly both diodes are going to connect for 180 degree. If you want in terms of time, then the conduction time of each diode is equal to T by 4, and similarly conduction time of both diodes is equal to 2 into T by 4, which is T by 2. Similarly, the conduction time of each thyristor is equal to T by 4, whereas the conduction time of both thyristors or both switches is equal to 2 into T by 4, which is T by 2. So with the help of this, we know the conduction angle and also the terms of time, the conduction time for each switch and the each diode, or simply both switches and both diodes. So we can say clearly that RMS value of the output voltage is equal to the RMS value of the output voltage is equal to peak value, which is VDC by 2. Whereas the conduction angle of each diode is equal to the conduction angle of each switch is equal to pi by 2, which is 90 degree. So simply we can say that the conduction angle of each diode is equal to the conduction angle of each thyristor is equal to pi by 2 is equal to 90 degree. Whereas the conduction angle of both diodes is equal to the conduction angle of both thyristor is equal to pi is equal to 180 degree. So simply we can say that the conduction angle of each diode is equal to the conduction angle of each switch is equal to 90 degree, whereas the conduction angle of both diode is equal to the conduction angle of both switches is equal to pi, which is 180 degree. So now we are going to draw what is the currents in the both the switches IS1 and IS2. So now we are going to draw what is the current in the switch S1, switch S2, diode D1 and diode D2. So what is the current we are going to see? As the switch S1 is connecting from only T by 4 to T by 2. Whenever the switch S1 is connecting, so output current is equal to switch current IS1. So therefore, whatever the output current in this region, it is going to follow the switch current also. So this is the nature of the switch S1 current. Similarly S2. So whenever the S2 is conducting, simply we can say that whenever the S2 is conducting, then IS2 is equal to minus I0 of t. So negative of the output current. So negative of the output current means this is the thing we are going to get. So only in this region the switch is connecting, and the remaining each and every region the switch is absent. So current is also 0. Whereas diode D1 is connecting only from 0 to T by 4. Whenever the diode D1 is conducting, the output current is, or you can say the current in the diode is negative of the output current. So from circuit diagram, so negative of the output current is like this we are going to get. So this is the diode D1, and the remaining regions diode D1 is absent. So therefore simply we can say that the current is equal to 0 in that range. Whereas diode D2 is conducting only from T by 2 to 3T by 4. Only in this range diode D2 is conducting. So if diode D2 is conducting, the output current is equal to the current in the diode. So therefore it is going to follow the output current. So this is the output current nature. So with the help of this, we have drawn the graphs for switch S1 current, switch S2 current, diode D1 current and diode D2 current. So now we are going to analyze each and every aspect of this one. So now we are going to find what is the average and the RMS value. So average and RMS value. So now the average value of the switch current is equal to, or simply thyristor current. So the average value of the thyristor current is equal to the average value of the diode current, because each and every graph is going to have the same area. So therefore the average value of the switch current is equal to the average value of the diode current is equal to, which is area, which is half into I naught max into, so half into I naught max into T by 4. So this is the area of that by total time period by capital T. So therefore area by capital time period, which is half into I naught max into T by 4 by T. So if you solve this one, we are going to get I naught max by 8. So this is called as the average value of the switch current or the thyristor current or simply diode current. Whereas if you want to find what is the RMS value of the switch current or the RMS value of the diode current, which is equal to, simply we have to do like this, under root over 1 by 2 pi into integration of 0 degree to pi by 2. So 0 degree to pi by 2 or 90 degree, the straight line, which is nothing but here we are going to get the slope. The slope is nothing but y-axis by x-axis, which is I naught max by which is here t by, or we can say pi by 2, because in terms of pi angle. So I naught max by pi by 2 into theta whole square into d theta. So 1 under root over 1 by 2 pi integration of 0 degree to 90 degree I naught max by pi by 2 into d theta into theta whole square into d theta. So if you solve this one, we are going to get finally I naught max by root 12. So I naught max by root 12 is the RMS value of the thyristor current or the RMS value of the diode current, which is I naught max by root 12. So if you want to know what is the fundamental, so as the output current is a square wave, or we can say the output current is a periodic signal. So if you expand in terms of Fourier series, we are going to get a fundamental component. So the fundamental component of the output current is equal to, which is the maximum value of the fundamental component of the output current into sine of omega t minus 90, because it is going to lag the source voltage by 90 degree. So therefore here the fundamental component of the output current is equal to the maximum value of the fundamental component of the output current into sine of omega t minus 90 degree. 01 indicates that it is the fundamental component of the output current. So I01 max simply indicates that this is called as the I001 t is equal to I01 max into sine of omega t minus 90 degree. So simply we can say that this is called as a fundamental component of the output current. So I naught of 01 t indicates that fundamental component of the I naught of t or simply output current. Whereas I01 max means simply we can say that it is a maximum value of the fundamental component of the output current. So I01 max is called as the maximum value of the fundamental component of the output current, which is I naught of 01 t. So now we are going to find what is the thyristor fundamental current. So thyristor fundamental current is equal to, or simply we can say that the switch fundamental current is equal to. So I want to find what is the fundamental current of the switch current. So is equal to, see, the fundamental current of the load current from 3 by 4 to T by 2. See, I am going to do for only the switch S1. So for switch S1 I am going to find this value. So therefore switch S1, so therefore it is equal to I naught of 01 t. So the fundamental current of the thyristor current is equal to the fundamental current of the output current for T by 4 to T by 2. So only for this region I am going to assume as S1 is going to connect. So this is the thing, it is going to happen. But for the remaining range from 0 to T by 4 and T by 2 to T, the remaining range, the switch S1 is not connecting. So therefore it is equal to 0. So simply we can say that here the fundamental component of the thyristor current is equal to fundamental component of the output current for T by 4 to T by 2, and it is equal to 0 for the remaining range. So IT01 of t indicates that this is the fundamental component of the thyristor current. So this is the fundamental component of the thyristor current. So this is the graph we are going to get for the fundamental component of the thyristor current. So IT01 of t is nothing but only from 90 degree to 180 degree it is going to present. So this is I01 of max. So and the remaining range it will be equal to 0. So this is the diagram we are going to get. So this is the basic diagram that we are going to get. So now I want to find what is the average value of the fundamental component of the thyristor current. So the average value of the fundamental component of the thyristor current is equal to 1 by 2 pi integration of 90 degree to 180 degree I01 max into sine omega t minus 90 degree into d theta. So IT01 of average is equal to 1 by 2 pi integration of 90 degree to 180 degree IT1 of I naught of 1 max into sine of omega t minus 90 into d theta. So if you solve this one, we are going to get, which is I01 max by 2 pi. So I01 max by 2 pi we are going to get. So I01 max by 2 pi we are going to get. So this is the thing we are going to get for the average value of the fundamental component of the thyristor current. So the average value of the fundamental component of the thyristor current is equal to I01 max by 2 pi. So if you want to find what is the RMS value of the fundamental component of the thyristor current is equal to under root over 1 by 2 pi integration of 90 degree to 100 degree I01 into sine of I01 max into sine of omega t minus 90 degree whole square into d theta. So if you solve this one, finally we are going to get, which is I01 max by 2 into root 2. So I01 max by 2 into root 2 is the RMS value of the RMS value of the thyristor, the fundamental component of the thyristor current we are going to get. See, for half wave rectifier, its average value is equal to peak value by pi, whereas the RMS value is peak value by 2. So here we have to go for division by 2, here division by root 2. So because it is half of the half wave rectifier. So for half wave rectifier, its average value is peak value by pi, whereas the RMS value is peak value by 2. So it is half of the half wave rectifier. So therefore here average value is divided by 2 and RMS value divided by root 2. So now we can say simply, see, same thing is going to occur for even, same measure is going to occur for even for diodes. So simply we can say that the average value of the fundamental component of the thyristor current or the average value of the fundamental component of the diode current both are same, which is equal to I01 max by 2 pi, where I01 max is called as the maximum value of the fundamental component of the output current. So therefore, whereas the IT RMS means the RMS value of the fundamental component of the thyristor current is equal to RMS value of the fundamental component of the diode current is equal to I01 max by 2 into root 2. So I've already told you this indicates that here RMS value of the fundamental component of the diode current. So RMS value of fundamental component of the diode current, whereas this indicates that the average value of the fundamental component of the diode current. Similarly, and this one indicates that here the RMS value of the fundamental component of the thyristor current, whereas this indicates that the average value of the fundamental component of the thyristor current. So 0, 1 indicates that it is the fundamental component of the respective current. So this is called as the RMS value of the fundamental component of the diode current, average value of the fundamental component of the diode current, whereas the RMS value of the fundamental component of the thyristor current, and this is the average value of the fundamental component of the thyristor current. So now we are going to analyze the output voltage and the output current with the help of Fourier series because they are periodic signals. So the output voltage is equal to sigma n is equal to 135 up to infinity 4 into the peak value is VDC by 2 by n pi into sine of n omega t or n omega naught t. So finally we are going to get sigma n is equal to 135 up to infinity 2 VDC by n pi into sine of n omega naught t, where omega naught is equal to 2 pi by capital T. So now I want to find what is the output current I want to figure out. So output current is equal to output voltage by XL. So finally we are going to get sigma n is equal to 135 up to infinity 2 VDC by n pi into here XL means simply we can say that n omega naught L. So n omega naught L because XL is equal to omega L indicates that here n omega naught L. So therefore XL is equal to omega L, whereas omega is equal to n omega naught because it's harmonic frequency. So n times the fundamental. So n omega naught L. So in place of XL substitute here n omega naught. So n omega naught L. So you are going to get n pi into n omega naught L is nothing but n square pi omega naught L into sine of. So n omega naught T minus n pi by 2. So n omega naught T minus n pi by 2 means take n as a common. So we are going to get omega naught T minus pi by 2. So this is the output current that we are going to get. So I want to find what is the fundamental component of the output current. Fundamental component of the output current means substitute here n is equal to 1. We are going to get 2 VDC by pi omega naught L sine of omega naught T minus pi by 2. So this is called as the fundamental component of the output current, which is 2 VDC by pi omega naught L into sine of omega naught T minus pi by 2. So this we can say it as a fundamental component of the output current. So now I want to find what is the maximum value of the fundamental component of the output current. So maximum value of the fundamental component of the output current is equal to, so the maximum value of the fundamental component of the output current is equal to 2 VDC by pi omega naught L. So 2 VDC by pi omega naught L is called as the maximum value of the fundamental component of the output current, which is 2 VDC by pi omega naught L. So fundamental displacement factor. So fundamental displacement factor means here it is a phase angle between the fundamental output voltage and the fundamental output current. So fundamental output voltage expression is very simple. So fundamental output voltage means substitute n is equal to 1. So we are going to get 2 VDC. So 2 VDC by pi into sine omega naught t. Whereas the fundamental output current is substitute n is equal to 1. We are going to get 2 VDC by pi omega naught L into sine of omega t minus pi by 2. So the phase angle between them is only pi by 2. So cos of pi by 2 means cos of 90 is equal to 0. So this is the fundamental displacement factor, which is equal to 0 degree. So if you want to find what is the output power due to the fundamental components. So what is the output power due to fundamental components? So simply we can say that the fundamental component of the output active power, because of fundamental components, how much amount of output power is absorbed by the load. So the output power is equal to V01 RMS into I01 RMS into cos of phi 1, means the RMS value of the fundamental component of the output voltage into the RMS value of the fundamental component of the output current into cos of phi 1. So is equal to, as cos phi 1 is equal to 0, so therefore overall value is going to become 0. So therefore simply we can say that the fundamental component of the output power is equal to 0. So if you want to find how much amount of fundamental component of the output reactive power is consumed by the load, so Q 1 is equal to the RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the output current into sine of phi 1. Whereas sine of phi 1 is nothing but 1. So now V01 RMS into I01 RMS. As you already know, what is the RMS value? So what is the RMS value of the fundamental component of the output voltage, which is 2 VDC by pi by root 2. So therefore simply we are going to get, so 2 VDC by pi by root 2. So this is the thing that we are going to get for the fundamental component of the output voltage. Whereas the fundamental component of the output current maximum value 2 VDC by pi omega naught L by root 2. So this is the thing that you are going to get. So this is the RMS value of the fundamental component of the output voltage, output current. So now this indicates that the fundamental component of the output reactive power. So from 0 to t to t by 2. So from 0 to t by 2, we can say clearly, so output voltage is equal to, VDC by 2 in this region. So therefore from 0 to t by 2, so simply we can say that here for 0 to t by 4, D1 is conducting, and from t by 4 to t by 2, S1 is conducting. So therefore the output voltage is always equal to VDC by 2. So therefore now if you want to apply the voltage and current relation across the inductor, which is V0 of t is equal to L into d I 0 of t by dt. So V0 is equal to L into d I 0 by dt. So for 0 to t less than t by 2, here output voltage is always equal to source voltage, which is VDC by 2. So L into d I 0 by dt means the maximum, the rate of change of the output current is from I 0 max minus I 0 max by the time period is here t by 2. So in this region, so therefore simply you are going to get VDC by 2 is equal to L into 2 I 0 max by t by 2. So this much amount of change in the output current in the time of t by 2. So if you solve this one, we are going to get I 0 max is equal to VDC by 8L into t. So VDC by 8L into t. This is the thing that we are going to get. So I 0 max is equal to VDC by 8L into t. So therefore the output voltage is equal to L into d I 0 by dt. So V0 in this from 0 to t by 2, the output voltage is equal to VDC by 2 is equal to L into 2 I 0 max by t by 2. So if you solve this one, we are going to get I 0 max is equal to VDC by 8L into t. So remember this small concept here. So this is the half wave rectifier, and this is the half wave rectifier. So therefore for half wave rectifier, the average value is equal. Let me assume this is the voltage V1. So the average value of this one for the first signal V1 is nothing but Vm by pi. Whereas this is half of the half wave rectifier. So here its average value is equal to, just if you want the average value of this one, go for half of this one. So therefore Vm by 2 pi. So this is called as the average value. So remember this small concept. So this is half of the half wave rectifier, and this is also half of the half wave rectifier. If you add these two signals, we are going to get this signal, which is the half wave rectifier. So half of the half wave rectifier plus half of the half wave rectifier if we add these two signals, we are going to get a half wave rectifier. So I want to find, see, these signals are of both same nature, so RMS value is same. So RMS value of this I1 current is I1, and the RMS value of this I2 is also again I1. So now I want to find what is the RMS value of this one, because RMS value is nothing but half wave rectifier is peak value by 2, peak value by 2. So therefore simply go for like this, is under root over I1 square plus I1 square is equal to Im by 2. So under root over I1 square plus I1 square is equal to Im by 2. So if you solve this one, we are going to get, so I1 is equal to Im by 2 root 2, or simply, so if this is the RMS value of this half wave rectifier, so if you want the RMS value of this one, means just go for the division by root 2. So Im by 2 root 2 you are going to get. This is the RMS value of this, both these graphs, half of the half wave rectifier. So if you want the average value half of the half wave rectifier, if you want the RMS value, which is 1 by root 2 times the half wave rectifier RMS value. So omega naught is nothing but 2 by f naught, or simply 2 by t. So always you can see clearly. So from the graphs we can see clearly that the maximum value of the fundamental output current is equal to 2 VDC by pi omega naught L. So that is called as the maximum value of the fundamental component of the output current. Whereas the maximum value of the output current is VDC by 8L into T. So VDC into T by 8L. So VDC into 8 T by 8L. So by comparing these two things, we can simply say that always. So we can always say that this value is always less than I naught max. So the fundamental component of the output current maximum value is always lesser than the output current of the maximum value of the output current. So the maximum value of the fundamental component of the output current is always lesser than the maximum value of the output current. So this is the relation that you need to easily remember. So now we are going to learn for the RL load. So for the RL load, now we are going to discuss the concept. So just we have replaced the L load by the RL load. So same as the previous circuit, just we replace the L load by RL load. VDC by 2, VDC by 2, switch S1, switch S2, diode D1 and diode D2. So the output voltage is plus or minus V naught of T, and the output current is I naught of T. And this is the IS is called as the source current. These are the switch current IS1 and IS2. So this is the source current IS. So now we are going to basically solve this numerical, or you can say we are going to basically understand this concept of this circuit. So now we are going to analyze this circuit. As I have already told you, for any load, irrespective of the load, I have already told you, when S1 is conducting, the output voltage is positive and the output current is also positive. Whereas when the D1 is connecting, so when D1 is connecting, the output voltage is positive and the output current is negative. Similarly, when S2 is conducting, from the circuit diagram we can say that the output voltage is negative and the output current is negative. Whereas when diode D2 is conducting, then we can say that the output voltage is negative and the output current is positive. So these are the things that we can understand from the circuit diagram. As I have already told you, irrespective of the load, for a voltage source inverter, its output voltage will be always constant graph. So therefore same graph for irrespective of the loads. So for 0 by t by 2, its value is equal to plus VDC by 2, whereas from t by 2 to t, its value is equal to minus VDC by 2. So this is the output voltage that we are going to get for a single phase average voltage source inverter irrespective of the load. But if you are going to give a current, a DC voltage for a RL load, then what is going to happen? So if you give a DC voltage across a RL load, then the current will be exponentially increasing. So here it is a lagging nature also. So it is going to lag by some amount of angle phi 1. So let me assume phi 1 is the angle by which the current is going to lag the supply voltage by. So therefore phi 1. So this is the current that you are going to get. So this is the current you are going to get. So this is phi 1 means this is phi plus phi 1, and this is a 2 pi. So this is the current, output current you are going to get. So this is the nature of the output current. Because current should lag. So as it is exponential, and it should also lag. So like this it is going to, you are going to get. This is phi 1 means this is phi, and this is phi plus phi 1. Because t by 2, for each t by 4 is nothing but 90 degree. So now from this you can see clearly from 0 to phi 1. So from 0 to phi 1, voltage is positive, and also the voltage is positive and also current is negative. So voltage is positive and the current is negative means simply D1 is connecting here. So D1 is going to connect here. So D1 is going to connect here. Whereas from 5 to 5, whereas from 5 to 5, the output voltage is positive and the output current is also positive. So both are positive means S1 is connecting. So both are positive means S1 is connecting in this region. Whereas from pi to 3 pi by 4 or simply pi to 3 pi by 4, here you can see clearly voltage is negative and the current is positive. So voltage is negative and the current is positive means D2 is connecting. So D2 is connecting. Whereas from 3t by 4 to t, here voltage is negative and the current is negative. So both are negative means simply S2 is connecting. So simply we can say that from 0 to 5 1, D1 is connecting. From 5 to 5, S1 is connecting. Whereas from t by 2, so t by 2, or we can say simply pi 2 pi plus phi 1. In this region, diode D2 is connecting. Whereas from pi plus phi 1 to 2 pi, 5 plus phi 1 to 2 pi, we can say that S2 is connecting. So from 0 to phi 1, D1 is connecting, and from phi 1 to phi, S1 is connecting, and from phi to 5 plus phi 1, D2 is connecting, and from 5 plus phi 1 to 2 pi, S2 is connecting. So this is the nature of the output current that we are going to get. So you can see clearly from 0 to phi 1 or phi. So you can go for anything. 0 to phi 1, D1 is connecting, and from phi 1 to phi, S1 is connecting, and from pi to pi plus phi 1, D2 is connecting, and from pi plus phi 1 to 2 pi, S2 is connecting. So now we are going to find what is the RMS value of the output voltage. So RMS value of the RMS value of the output voltage is equal to peak value, which is VDC by 2, whereas the conduction angle of each diode is equal to. So the conduction angle of each diode is equal to phi 1, as we have already seen in the figure. So the conduction angle of the conduction angle of each diode is equal to phi 1. So conduction angle of each diode is equal to phi 1. From the graph only we can see that one. Whereas the conduction angle of both diodes is equal to 2 phi 1, because phi 1 is the conduction angle for each and every diode, because there are 2 diodes, so 2 into phi 1. Then what is the conduction angle of each thyristor? So in 0 to 5, phi 1 is for D1, so therefore pi minus phi 1 is for the pi minus phi 1 is the conduction angle of each and every switch or each and every thyristor. So conduction angle of each switch or each thyristor is equal to pi minus phi 1. So if you want both thyristors, just 2 times of pi minus phi 1. So the conduction angle of each diode is equal to phi 1, whereas the conduction angle of each switch is equal to pi minus phi 1. So now as the output voltage is a periodic signal, so we can apply the Fourier series. So output voltage is equal to sigma n is equal to 135 up to infinity 4 into the peak values VDC by 2 by n pi sine of n omega naught t, where omega naught is equal to 2 pi by capital T, or simply 2 pi f naught. So if you solve this one, we are going to get finally sigma n is equal to 135 up to infinity 2 VDC by n pi into sine of n omega naught t. So if you want the output current, so basically if you want the output current, what is going to happen? So if you want the output current, then simply sigma n is equal to 135 up to infinity. So 2 VDC by n pi, 2 VDC by n pi. So 2 VDC by n pi by Zn. Zn we are going to write sine of n omega naught t minus phi n. N omega naught t minus phi n. So this is the thing we are going to get. So 2 VDC by n pi Zn sine of n omega naught t minus phi n. Zn is equal to under root over r square plus omega l is n omega naught l whole square. So Zn is equal to under root over r square plus n omega naught l whole square. Whereas phi n is equal to do the ratio of these things, tan inverse of n omega naught l by r. So n is a constant, we can take it outside. So n into tan inverse of omega naught l by r. So therefore simply you are going to get like this. So Zn is equal to under root over r square plus n omega naught l whole square, whereas phi n is equal to tan inverse of n omega naught l by r. So n is a small n is a constant, you can take it outside. So phi n is equal to n into tan inverse of omega naught l by r. So this is the equation that you are going to get finally. So I naught of t is equal to sigma n is equal to 3 pi up to infinity 2 VDC by n pi Zn sine of n omega naught t minus phi n, whereas Zn is equal to under root over r square plus n omega naught L whole square, whereas phi n is equal to n into tan inverse of omega naught L by r. So if you want to find what is the fundamental component of the output current, so fundamental component of the output current is equal to, substitute here n is equal to 1, you are going to get 2 VDC by pi Z1 sine of omega naught t minus phi 1. So if you substitute n is equal to 1 in this expression, you are going to get the fundamental component of the output current. So therefore, this is the maximum value of the fundamental component of the output current into sine of omega naught t minus phi 1. So Z1 is equal to, in place of this expression, substitute n is equal to 1, you are going to get under root over r square plus omega naught L whole square. Similarly, phi 1 is equal to tan inverse of, substitute here n is equal to 1, we are going to get tan inverse of omega naught L by r. So this is the expression that you are going to get for the fundamental component of the output current. Means you have to substitute n is equal to 1 in this overall expression, you are going to get all these crazy things that you are going to get finally. So fundamental displacement factor is equal to cos of phase angle between the fundamental output voltage and the fundamental output current. So the fundamental output voltage is, substitute n is equal to 1, 2 VDC by pi sine of omega naught t, whereas here if you substitute here n is equal to 1, we are going to get, this is the expression that we are going to get. The phase angle is nothing but here phi 1. So cos of phi 1 is the fundamental displacement factor. Phi 1 is the phase angle between the fundamental output voltage and the fundamental output current. So now we are going to find what is the fundamental component of thyristor current. So IT01 of T means the fundamental component of the switch current or the thyristor current. So all fundamental component of thyristor current. Whereas IT01 of T means it is a fundamental component. It is a fundamental component. It is a fundamental component of the diode current. So therefore fundamental component of the diode current. So we are going to find these things. So the RMS value and the average value. So if you want to find what is the RMS value of the fundamental component of the thyristor current, so RMS value of the fundamental component of the thyristor current, so IT01 RMS means the RMS value of the fundamental component of the thyristor current. Because the switch S1 is connecting from only phi 1 to phi. The switch S1 is connecting only from phi 1 to phi. So switch S1 is connecting only from phi 1 to phi. Only in this range it is equal to, means only in phi 1 to phi. So we can say that only from phi 1 to phi, only from phi 1 to phi it is equal to the fundamental component of the thyristor current is equal to fundamental component of the output current only in this range, and in the remaining ranges it is equal to 0. So therefore 1 by 2 pi under root over 1 by 2 pi integration of phi 1 to phi. Here we have to go for the fundamental component of the output current, which is I of 01 max sine of omega naught t minus phi 1 whole square into d theta. So this we are going to get the RMS value of the fundamental component of the thyristor current. So therefore now we can say that here the RMS value of the fundamental component of thyristor current is equal to 1 by 2 pi, because the switch S1 is connecting only from pi 1 to pi. So in that range we can say that whatever the thyristor fundamental current is equal to the fundamental component of the output current. So therefore I01 max sine of omega naught t minus phi 1 whole square into d theta. So under root over. So this is the way that we are going to get the RMS value of the fundamental component of the thyristor current. Similarly, the RMS value of the fundamental component of the diode current is equal to under root over 1 by 2 pi integration of, because diode D1 is connecting only from 0 to phi 1. So 0 to phi 1. So whenever the diode D1 is connecting, the output current is the output, or you can say the current in the diode D1 is equal to, the current in the diode D1 is negative of the output current. It is a negative of the output current. So therefore simply we have to go negative of that one, or simply negative of that one, we have to do this one. But here in that range, if you do negative also, same thing you are going to get, again square of that, it is going to give you same result. So under root over 1 by 2 pi 0 to phi 1 minus I01 max sine of omega naught t minus phi 1 whole square into d theta. So by this we are going to get basically the RMS value of the fundamental component of the diode current. So we can say simply this indicates that the RMS value of the fundamental component of the switch current, and this indicates that the RMS value of the fundamental component of the diode current. So now I will draw the fundamental output voltage and the fundamental output current. The fundamental output voltage expression I have already told you in a very detailed manner. The fundamental output voltage expression is equal to 2 VDC by pi sine omega naught t. So this is the, we are going to get 2 VDC by pi sine omega naught t is the fundamental output voltage. Similarly, I want to find the expression of the fundamental output current is equal to, here I naught 1 max into sine of omega naught t minus phi 1. So this is the graph we are going to get. So this is the graph that we are going to get for the fundamental component of the output current. So now I have already told you switch S1. Switch S1 is connecting only from phi 1 to phi. Only from phi 1 to phi it is going to connect. So whatever the fundamental component of the switch current is equal to fundamental component of the output current only in this range, and in the remaining range it is equal to 0. Similarly, diode D1 is connecting only from 0 to 5. So whatever the fundamental output current in this range is equal to the current in the diode. So this is the way that we need to do this one. As actually it is a negative value, so you have to go in this positive sense. So it will be actually a positive value because only a positive things are going to present in the current. So basically actually the graph should be from, because positive, because whenever the diode D1 is connecting, the output, we can say the current in diode is negative of this, the negative of the output current. So here negative has to be, means it will be upper here. But anyhow, we are going to get the same average value and the same RMS value, even if it is negative or positive graph. So now we are going to learn about the fundamental power across load, means how much amount of fundamental power is absorbed by the load we need to figure out. So the fundamental power absorbed by the load is equal to RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the output current into cos of, we can say phi 1. Phi 1 is the phase angle between the, phi 1 is the phase angle between the fundamental component of the output voltage and the fundamental component of the output current. So the RMS value of the fundamental component of the output voltage is 2 VDC by pi root 2. So you are going to get finally root 2 VDC by pi. Whereas the RMS value of the fundamental component of the output current, which is simply we can say that 2 VDC by pi Z1 by root 2. So you are going to get root 2 VDC by pi Z1. So if you want phi 1, so we know the phi n is equal to n into tan inverse of omega naught L by R. So here n is equal to 1. If you substitute, we are going to get tan inverse of omega naught L by R. So this is the expression that you are going to get finally. So if you substitute all these three things here, you are going to get the fundamental power absorbed by the load. Similarly, I want to find what is the fundamental reactive power absorbed by the load. Same thing, the RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the output current into sine of phi 1. So each and every value we know, just substitute here and you will get the solution. So you can see clearly, suppose for 360 degree I am assuming t seconds. So for 360 degree means I am going to assume t seconds. So for 1 degree it will be t by 360 degree. So if you divide by 360 degree on both sides, you are going to get 1 degree is equal to t by 360 degree seconds. So for phi 1 degree means in multiply by phi 1 on the both sides, we are going to get t into phi 1 by 360 degree. So this much amount of seconds. Therefore here suppose here you can see clearly means for phi 1 degree means if you want to convert in terms of seconds, so phi t into phi 1 by 360 degree. So by this way we can convert phi 1 into in terms of seconds. So you can see clearly the output power is positive, means when either the voltage is positive or either the voltage is negative or the current is negative. So you can see clearly from 0 degree to phi 1 degree. So from 0 degree to phi 1 degree, here voltage is positive and the current is negative. So if you do the product, we are going to get power as negative. Similarly from 180 to 180 plus 5. So here also voltage is negative and the current is positive. So therefore if you do the product, we are going to get power as negative. So from 0 degree to phi 1 degree and from 180 degree to 180 plus phi 1 degree, in both these ranges the output power is negative. Whereas in the remaining ranges from phi 1 to 180 degree, the output voltage is positive and the output current is positive. So therefore simply we can say if both are positive, the power is also positive. Similarly from 180 plus phi 1 to 360 degree, the output voltage is negative and the output current is negative. So their product is also equal to positive. So therefore simply we can say that power is positive in these two ranges. So power is equal to negative. The output power is negative means load is delivering power to source. If P0 is equal to negative means the load is power is negative means it is basically sending power to the source. If P0 is equal to positive means the load is absorbing power from the source. So P0 is equal to positive means the load is absorbing power from the source, and P0 is equal to negative means the load is delivering power to the source. So P0 is equal to negative means load is delivering power to the source, whereas P0 is equal to positive means source is delivering power to load. So now we are going to study about the RLC load. So this is the RLC load. In the previous we have learned about the RL load. So now we are going to study the RLC load. So you can see clearly this is called as the single phase off bridge voltage source inverter. So in the previous we have studied RL. So now we are going to keep the RLC load. So VDC by 2, switch S1, switch S2, diode D1 and diode D2. So this is the load we are going to connect, which is the RLC load. The output voltage is plus or minus V0 of t and the output current is I0 of t. So now we are going to analyze this circuit. As I have already told you from the earlier onwards, here for any load, when switch S1 is connecting, the output voltage is positive and the output current is positive. Whereas when diode D1 is connecting, the output voltage is positive and the output current is negative. Whereas when switch S2 is conducting, the output voltage is negative and the output current is also negative. Whereas the diode D2 is connecting, the output voltage is negative and the output current is positive. So this is the nature of each and every output voltage and output current. So based on these different types of connecting of the switches. I already told you the output voltage is always same irrespective of the load. So the output voltage is always same irrespective of the load. So from 0 to t by 2, its value is plus VDC by 2, whereas from t by 2 to 3t by 4, or you can say from t by 2 to t, the output voltage is minus VDC by 2. So this is the output voltage that we are going to get. From 0 to t by 2, it's plus VDC by 2. From t by 2 to t, its value is minus VDC by 2. So now I want to find what is the output current. So based on this, I want to find what is the output current. As I have already told you, irrespective of the load, the output voltage is same, but only thing the current is going to get changed. So when XL is greater than XC, what is going to happen? The inductive reactance is more than the capacitive reactance. So overall circuit is going to act like an inductive circuit. So therefore the current is going to lag the supply voltage. So the current is going to lag the supply voltage in this fashion, which is from here 5 to 5 plus 5 and is going to be like this. So this is the fashion of the current we are going to get. It's a lagging amount of current we are going to get. So it is a sinusoidal, because if you give a pure DC for RLC, we are going to get nearly a sinusoid curve we are going to get. Whereas when XL is less than XC means, whenever the XL is less than XC means, simply we can say that whenever the XL is less than XC means, simply we can say that the capacitor. So I have already told you, whenever the XL is less than XC means the capacitor reactance is greater than the inductive reactance. So the circuit is going to act like a capacitor circuit. So therefore the current is going to lead the supply voltage. So if this is phi 1, it will be pi minus phi 1, and this is 2 pi minus phi 1. So this is the way we are going to get the graph. As we are going to give a DC supply across any RLC, we are going to get a sine wave. So therefore this is the graph we are going to get. So you can see clearly, this is called as, when XL is greater than XC means, this we call it as the overdamped system. Whereas XL is less than XC means, we can say it is a underdamped system. So this is the overdamped system and this is the underdamped system. So you can see clearly from 0 to phi 1. So this is 0 to phi 1. So if 0 to phi 1 means this is pi and this is phi plus phi 1, and here this is 2 pi. So if this is phi 1, it will be pi minus phi 1 and this is 2 pi minus phi 1. So like this we are going to get. It's like a pure sine wave we are going to get. This is lagging and this is leading. So it is the only difference. So you can see clearly from 0 to phi 1. So from 0 to phi 1, the output voltage is positive and the output current is negative. So we can say diode D1 is connecting here. Whereas from phi 1 to phi, the output voltage is positive and the output current is also positive. So switch S1 is connecting. Similarly, from pi to pi plus phi 1, the output voltage is negative and the output current is positive. So diode D2 is conducting. Whereas here from pi plus phi 1 to 2 pi, we can say that output voltage is negative and the output current is also negative. So switch S2 is conducting for this overdamped system. Whereas for here, for the undamped system, when XL is less than XC, you can see clearly from 0 to phi 1. So from 0 to, or you can say from 0 to, so from 0 to pi minus phi 1, from 0 to pi minus phi 1, you can simply say that the voltage is positive and the current is positive. If both are positive, means we can say S1 is connecting. Whereas from pi minus phi 1 to 2 pi, whereas pi minus phi 1 to pi, voltage is positive and the current is negative. So voltage is positive and the current is negative means diode D1 is connecting. Again from pi to 2 pi minus 5, whereas pi to 2 pi minus phi 1, here the voltage is negative and the current is also negative. So both are negative means switch S2 is connecting. Similarly from 2 pi minus phi 1 to 2 pi, both the voltage is negative and the current is positive. So we can say that switch D2 is connecting. So this is the range of each and everything. So if you know the graph, then you can easily figure out where are the switches are going to get conduct. Also commutation is required for thyristors in lagging load condition. So fourth commutation is required for thyristors in lagging load condition. See, in the lagging load condition means XL is greater than XC, XL is greater than XC. So here XL is greater than XC means you can see clearly in the graph. So for XL greater than XC, whenever the D1 is connecting, so whenever the D1 is connecting, then the S1 is going to conduct. Means simply we can say that, see, the S1 is going to conduct only when D1 is off. So therefore again S1, so therefore then we are going to turn on the D2. So therefore here forced commutation means we have to off the switch S1, then only we have to on the D2. So simply we can say that here after S1 you have to turn on the D2, so you have to off it. So forced commutation is required for turning off the thyristors. So then only we can on the remaining switches. So we can say that forced commutation is required. Forced commutation is required only in the lagging condition, whereas in the leading condition you can see clearly. See, when is D1 is on, so when the D1 is on, default a negative voltage is going to apply across the switch S1. So therefore simply we can say that switch S1 is going to get turned off. Similarly here, when D2 is on, at that instant a negative voltage is going to apply across switch S2. So therefore the switch S2 is going to get turned off. So no need of forced commutation to turn off the thyristors on the switches. So whereas here, yes, you need to forcefully turn off the thyristors. Whereas here, by default, their parallel diode is going to get conduct. Whenever it is going to conduct, it is going to produce a negative voltage across the switch. So therefore, it is going to get turned off. So for a forced commutation is required for turning off the thyristors for the overdamped system, whereas no need of any forced commutation switches for turning off the switches in the underdamped system. So forced commutation is required for thyristors in lagging load condition, whereas natural commutation is happened for thyristors in leading load condition. Means we have to keep an extra circuit in order to forcefully turn off the switches in the lagging condition, whereas in the leading condition, by naturally they are going to get turned off because of their parallel diodes. So natural commutation is happened for thyristors in the leading load condition. So now in both the cases, in both the graphs for overdamped system and underdamped system, the conduction angle of each diode is phi 1. The conduction angle of each diode is phi 1 in both the graphs. You can see clearly. And also the conduction angle of each switches or thyristor in both the graphs, which is pi minus phi 1. So pi minus phi 1 is the range for each switch or each thyristor is going to conduct in both the graphs. So you can see clearly phi 1 is the angle for which the diodes is conducting for overdamped and also in the underdamped. So we can say clearly phi 1 is the angle for which the diodes are going to conduct, whereas pi minus phi 1 is the range for which the thyristors are going to conduct. So this is for both the cases. So now I want to find what is the circuit turn-off time. Circuit turn-off time means the time for which the negative reverse bias voltage is applied. So I have already told you only in the underdamped system, is XL less than XC. So when the XL is less than XC only, it is called as underdamped system. So only in that case, whenever their anti-parallel diode is going to conduct, means then only in that range this diode is going to produce a negative voltage across that switch. So therefore it is going to get turned off. So for D1 is connecting for a range of only 5. So phi 1 by omega. So phi 1 by omega naught is the circuit turn off time for which a reverse bias voltage is going to apply across the thyristors. So phi 1 by omega naught. So if you want phi 1, which is tan inverse of omega xc minus xl by r magnitude value. So therefore phi 1 is equal to tan inverse of xc minus xl by r, where xc is equal to 1 by omega c, xl is equal to omega l. So Cc is equal to phi 1 by omega naught. Phi 1 is equal to tan inverse of xc minus xl by r magnitude. So now I want to write what is the Fourier series expansion for the output voltage. As the output voltage is a periodic waveform, so therefore V naught of t is equal to sigma m is equal to 135 up to infinity 4 into the peak value, which is VDC by 2 by n pi sin n omega naught t. So if you solve this one, we are going to get sigma n is equal to 135 up to infinity 2 VDC by n pi into sin of n omega naught t. So if you want the output current, general expression, which is sigma n is equal to 135 up to infinity 2 VDC by n pi magnitude of the Zn sin of n omega naught t minus phi n. So therefore this by mod of Zn minus phi n. So I naught of t is equal to sigma n is equal to 135 up to infinity 2 VDC by n pi magnitude of Zn sin of n omega naught t minus phi n, where magnitude of Zn is equal to under root over r square plus xl is nothing but n omega naught l minus 1 by n omega naught c whole square. So mod of Zn is equal to under root over r square plus n omega naught l minus 1 by n omega naught c whole square, whereas phi n is equal to tan inverse of, which is xl minus xc by r, which is n omega naught l minus 1 by n omega naught c by r. So like this you are going to get. So this is called as a phi n. So phi n is equal to tan inverse of n omega naught l minus 1 by n omega naught c by r. So if you want to find what is the fundamental, or we can say fundamental component of the output current is equal to, so if you substitute n is equal to 1 in the general expression, we are going to get finally 2 VDC by pi of magnitude of Z1 sin of omega naught t minus phi 1. So here Z1 is equal to magnitude of Z1 is equal to under root over r square plus omega naught l minus 1 by omega naught c whole square. Similarly phi 1 is equal to substitute n is equal to 1, we are going to get tan inverse of omega naught l minus 1 by omega naught c by r. So this is the angle phi 1. So this is the angle phi 1 we are going to get. So this is basically the angle phi 1 we are going to get. So I want to find what is the maximum value of the fundamental component of the output current, which is 2 VDC by pi of mod of Z1, where mod of Z1 is equal to under root over r square plus omega naught l minus 1 by omega naught c whole square. I have already told you fundamental displacement factor is equal to cos of phase angle between the fundamental output voltage and the fundamental output current. So cos of phi 1, because the fundamental output voltage is 2 VDC by n pi by pi sin of omega naught t, and the fundamental output current is this one. So the phase angle is phi 1. So therefore cos of phi 1 is the fundamental displacement factor. So now we are going to see the fundamental diode and the fundamental switch current. The fundamental diode current and the fundamental switch current we are going to see. Fundamental diode current and the fundamental switch current. See, I want to draw what is the fundamental diode current and the fundamental switch current. As I have already told you, the switch diode D1 is connecting only from 0 to phi 1. For overdamped case, I am going to draw the graph. So for overdamped case, I have already told you, for 0 to phi 1, the diode D1 is going to connect. So whenever the diode D1 is connecting, the diode current is equal to negative of the output current. So therefore, see, I have drawn like this, but it's a negative, means it is going to flow in this manner. So this is called as the only in this range it is equal to fundamental component of the output current, and the remaining range it is equal to 0. Similarly, thyristor, the fundamental component of thyristor current is equal to only from phi 1 to pi, the switch S1 is connecting. So only in this range the fundamental component of thyristor current is equal to fundamental component of the output current. So fundamental component of the output current you are going to take here, and in the remaining range it is equal to 0 because it is not conducting. So if you want to find what is the average value of the fundamental component of the diode current is equal to 1 by 2 pi integration of 0 to phi 1, you have to go for the value of the fundamental output current, which is I naught 1 max into sine of omega naught t minus phi 1 into d theta. So if you want to find what is the RMS value of the fundamental component of the diode current, which is under root over 1 by 2 by integration of 0 to phi 1 I naught 1 max into sine of omega naught t minus phi 1 whole square into d theta. So you are going to get like this. So if you want to find what is the average value of the fundamental component of thyristor current is equal to 1 by 2 pi integration of pi 1 to pi, in that range only the fundamental component of the thyristor current is equal to fundamental component of the output current, which is I naught 1 max into sine of omega naught t minus phi 1 into d theta. Similarly, if you want the RMS value of the fundamental component of thyristor current is equal to under root over 1 by 2 pi integration of pi 1 to phi I naught 1 max into sine omega naught t minus phi 1 whole square into d theta. So IT01 of t means the fundamental component of the diode current. IT01 t means the fundamental component of thyristor current, whereas IT01 of average means the average value of the fundamental component of the diode current, whereas IT01 RMS means the RMS value of the fundamental component of the diode current. IT01 average means the average value of the fundamental component of thyristor current, and IT01 RMS means the RMS value of the fundamental component of the thyristor current. So this easy way to remember this graph is simply this is OU, like Usmania University. So first is overdamped and the next is underdamped. So XL is greater than XC and XL is less than XC. So OU, Usmania University. So OU, overdamped and underdamped. So by this we have completed. So by this concept we have completed the single phase half bridge voltage source inverter with R load, with L load, with RL load and also RLC load. All these 4 loads we have studied in very detailed manner.